Welcome back to Computer Graphics. So today we're going to switch gears. We've wrapped up our discussion of rendering, and we're moving on to talking about animation. So throughout the course of our whole class, we've been gradually increasing the complexity of our models. On the first day, we talked about how do we even describe a shape, a piece of geometry, and we talked about how to label the vertices and connect up the vertices of the cube. Then we said, well, we can use various kinds of geometric transformations to maybe build up something slightly more interesting. And then we really got deep into discussions of geometric representations, polygon meshes, implicit and explicit representations of geometry. More recently, we've been talking about materials and lighting. How do we add realistic shading to those geometric models? But so far, one thing that we haven't really talked at all about is adding motion, something that's very much a part of the world we live in. So how would we represent and how would we express complicated motion like we see in the real world, whether it's the motion of the body moving around, whether it's the motion of cloth being deformed, and all sorts of other things. If we go back through the history of mankind, we find that people have always been interested in depicting and capturing motion that they see in the real world. So this is perhaps what you might call the oldest animation or one of the oldest known animations. This is actually not originally animated, but just a drawing that's found on the side of an ancient vase. So somebody thought it was really interesting that this kind of goat creature hops up and eats the berries off the leaves of this tree. And here I've just taken the frames and composited them into an animated GIF. And we see this kind of thing, kind of throughout antiquity, people trying to use different still images to capture motion. So here may be different kinds of wrestling moves. Here's a drawing by Leonardo da Vinci, kind of picking up on the fact that as the body moves, there's also kind of secondary motion, bulging and swelling of the shape and size of muscle, maybe to preserve volume. Still with static images, we have painters like Claude Monet, impressionists, saying, if I really want to capture the spirit of being in this scene, then I should paint even a static image in a way that captures motion. So here we get the impression of the grass blowing around and the clouds moving. But so far, these are still just static images, right? Not really capturing motion as we normally experience it. So one of the first technological developments that kind of pushed us toward animation were devices like this one, the phenakistoscope. And the idea here is, again, you have a sequence of images that describes the motion, but this is played back by spinning this disc and watching it through a small slit. And the idea is that you're essentially taking advantage of aliasing to trick the eye, to trick a human observer into believing that motion occurs. So we'll talk a little bit about these perceptual issues today. Right? And the slit is needed in this case to avoid this thing from just being a blur when you look at it spinning. So we really want to capture snapshots of this disc at different moments. Kind of the first real film that was developed was this one done by Muybridge, who was trying to resolve a very simple question, which is when a horse gallops, do all four legs ever leave the ground at the same time? And to us today, this sounds like a really trivial thing to answer, but if all you can do is look at a horse with a naked eye and not really capture its motion, okay, this might be a tricky thing to answer. And so this was a technology that wasn't designed for entertainment or anything like that, but the technology still accelerated the development of animation. Of course, we know what happened after that. Once we had film, people started generating all sorts of beautiful animations. And probably if I asked you what is the first animation that was ever done on film, there's a natural impulse to say, oh yeah, that was probably Walt Disney, right? Well, actually, if you go back digging through the annals of history, you'll find lots of crazy, interesting examples of animation that happened before Disney came out. So here's a fun example of French animation, kind of drawn by hand onto film somehow. All sorts of fantastical things going on. okay, but this is just, a short little cartoon. And so if I ask you, okay, but what's the first feature-length animation? Then, of course, you know that this was done by Disney. Actually, it wasn't. The first feature-length animation was this totally out there thing called kind of the Adventures of Prince Ahmed. And this was done in a completely different way than animation we know today. This is actually almost kind of a puppet, so a bunch of rigid pieces that can be moved by an animator and then projected onto the film with all sorts of other wild effects going on here. Okay, but if I ask you what is the first hand-drawn feature-length animation, right? Well, that's something that finally Disney can lay credit to. You have to put a few qualifiers on there, but yeah, in some sense, Disney had the first hand-drawn feature-length animation, which was Snow White and the Seven Dwarfs, this very famous movie with beautiful hand-drawn animation. And if we continue going into the present or the near present, people are still doing just absolutely beautiful hand-drawn animation by drawing sequences of images that get played back, not so different from this kind of old-fashioned spinning device that we saw, right? But now starting to see probably a lot more digital technology coming into play, doing things like matting and coloring and so forth. How about animations that are computer generated? Right? These are still hand-drawn animations. So I ask you, what's the first computer-generated animation? Again, you might gravitate towards Disney, right? Maybe this was Toy Story or something. Well, again, if you really go digging, you'll find all sorts of interesting examples of animation people were making with a computer before, Pixar was on the scene. And again, it was really that there was some new technology that came out that enabled new modes of animation, right? So computers were really something that gave us new ways of thinking about how to animate. This is actually done with something that's more of an analog kind of computers. The first digital computer animation, again, was not yet Toy Story, but this is something called Sketchpad, developed by Ivan Sutherland. And this was a really landmark development in not only computer graphics, but also human-computer interaction and several other things of just being able to draw and manipulate graphics on the screen. Okay. What about the first 3D computer animation? Well, that was, I'm not sure exactly who gets to claim first, but there were definitely some interesting early animations. Again, not necessarily aimed at entertainment. So one of the early animations was done by Boeing, the Boeing Man, which was just trying to see how a pilot would behave in a cockpit. If you go over into the Soviet Union, you can find all sorts of strange and interesting things that were going on. This is an animation that was essentially one of the earliest examples of ASCII art. So this is a animation of a cat that's a bunch of printouts. This is paper that was printed out and captured with ordinary film. If we go over to University of Utah in the 70s, was doing a huge amount of work on early computer animation. This is done by Ed Catmull and Fred Park. Ed Catmull was one of the co-founders of Pixar, and we really start to see more sophisticated shading going on, starting to try to understand how to do realistic facial motion, human motion, although still not that realistic, right? Something we still struggle with actually in computer animation is making human faces that don't look slightly bizarre, slightly uncanny. Okay. What about the first feature-length computer animated film? Well, the first one that was attempted actually is this one called The Works that was done at the New York Institute of Technology. A lot of the early pioneers of computer graphics were hanging around there, Catmull, Heckbert, other folks. And they got pretty far into development for this thing, but still were at the point where compute power was holding them back. It just wasn't feasible to render all the frames of this animation. And now that you've had some experience developing a renderer, maybe you can appreciate why this was such a challenge. Right? Each frame can take a whole lot of compute power, many hours, just to generate one frame of animation. You have to generate at least, 24 frames per animation per second for a film quality movie. Okay. So eventually, kind of Moore's Law caught up, And Pixar was able to come out with the first successful feature-length computer-generated film, Pixar's Toy Story, which many of us know from this movie and its many sequels. Really quite impressive accomplishment, especially given the level of technology.
Starcommand, come in. Do you read me?
Early 1990s.
There seems to be no sign
And of course, we've continued to build on this technology since then and add all sorts of beautiful lighting effects, so a lot more now global illumination. Things that used to be faked in early computer graphics movies are really physically based, adding a lot of interesting animation, physically based animation and simulation, which we'll talk about in the next couple lectures, have been added to this story. Just some really gorgeous and creative stuff. Other, kind of interesting technologies that kind of come into play are keep happening. So before we saw a spinning image that gave us a sense of motion, here we have a solid object. Somebody's arranged these pieces on this kind of spinning dinner plate. And what's happening here is this is spinning, and also a strobe light is flashing. Right? And a strobe light is flashing again to kind of take advantage of aliasing to trick or fool the eye and the mind into believing that motion is occurring. So this is what's called a zoetrope. And now that we have sophisticated 3D printers, people are taking this same idea of this kind of spinning solid animation and using 3D printers to make some truly remarkable stuff. So this is a piece that's been 3D printed and carefully designed so that when it spins up to a certain speed, you don't get this jerky motion, but you get this really incredible organic motion. So if we give this a few seconds here, it'll kind of come up to the kind of stationary speed, and we'll see this organic movement. Right, this thing that really looks like it couldn't possibly be happening in front of our eyes. Okay, and so what we've seen is, at each stage, a little bit of technology has opened up a lot of doors into how we can present motion. And whenever we have a new technology, we have to answer the question of, okay, great, there's this amazing technology for showing motion, for showing animation. How do we generate it? How do we design it? How do we do the computation needed to build animation? And that's what we really want to get at. One thing that's really important to understand, as with many things in computer graphics, is the human perceptual things that lead us to understand motion. Right? So how do human beings experience motion? Well, one of the earliest theories, which has subsequently been debunked, is the idea that perception of motion comes from persistence of vision. So for instance, if you're out at nighttime and somebody's waving a flashlight around, you might see kind of a streak in your vision of where the flashlight used to be. And so this was a theory that perhaps all perception of motion is that there's actually this streak left really in your retina that tells you how things are moving. It turns out that's not really the case. The eye is really quite different from a camera. A lot of the analogies we might use from film and so forth don't really hold up. And so more modern psychological explanations are things like the beta phenomenon, that you do have this kind of persistence of motion, but that record of what was happening is kept not in the eyeball, but in the brain. So for instance, when we look at this animation on the bottom left, you get this sense that things are moving around, but okay, really things aren't moving around. We just have red lights turning off and on, right? There's no real motion, but it's this history, this visual memory that you keep in your brain that gives you this feeling or this perception that things are moving. There's also something called the phi phenomenon, which is that the brain anticipates emotion, that there are visual cues that you see in nature that makes you feel like motion is going to occur. And so here's kind of a cool optical illusion that takes advantage of this phi phenomenon. These two little kind of flowers on each side are actually rotating at exactly the same speed, but because the one on the right is flashing kind of black and white faster than the one on the left, you get this stronger sense of anticipation that it's going to move forward quickly, right? And even after the illusion has been explained to you, this phenomenon is so strong that you still can't help but see one of them moving faster than the other. And so you really get the sense that understanding these perceptual phenomena is really important when it comes to designing and building digital animation, right? To thinking about how you're going to craft these things. People have been taking advantage of these phenomena in art for many years, right? So the beta phenomenon is basically the phenomenon that lets us watch film. A sequence of still images gets perceived as motion because we have a visual memory in our brain of what happened previously. And in even static art like Monet or in Duchamp, there's this way of using different visual cues to suggest or cause the mind to anticipate what's going to happen and give a sense of motion. Okay. So in kind of traditional hand-drawn animation, how do we generate motion? And this is largely based around this beta phenomenon of showing several frames in sequence and taking advantage of visual memory. So to generate this motion, the senior artist, maybe at Disney, is going to sit down and draw some key frames. So some frames that highlight events that occur. Right? Okay, Captain Hook picks up his hook, then he puts it back down into his hand. And an apprentice will then sit down after the senior artist has drawn the keyframes and fill in the rest, draw in-betweens. So what are the smaller motions that get us between these keyframes? Obviously, if you're doing this by hand and you have to generate 24 frames per second, this is a very tedious and labor-intensive process. And so you think, well, anything that's a lot of fairly repetitive, rote task that has a reasonably straightforward description or something that could be boiled down into an algorithm, that's a real opportunity for technology to step in and automate things that we'd rather not do ourselves. So how can we describe motion on a computer that takes advantage of computation to take care of the tedious stuff for us? Well, there are a lot of different basic techniques for computer animation. One of them looks very much like traditional hand-drawn animation, this idea of keyframing. So we have, rather than a drawing now, we have a 3D model or a rig, so kind of a 3D model with a lot of different handles that we can tweak and adjust. And we might turn some of these handles to put the character in various keyframes, but then rather than having another person come in and come up with the in-betweens by tweaking the handles some more, we actually just let the computer somehow interpolate between these different configurations. And we'll talk about that today. A different class of methods is to use data to generate animation. To use, for instance, something like motion capture. So this is a photograph from the CMU motion capture studio. And what's going on here is somebody's wearing this dark garment with these bright white balls glued to various locations. And there are cameras in various locations around the room that pick up on these balls. So take pictures of the person wearing this funny suit from various angles, and by triangulating these points, you can figure out how the person is configured, where they're moving their arms and legs at any given time. You record this over time, and you get an animation, or at least you get a record of how the joints in the body move. Then you can take this data, how these joints are moving around, and map it onto a character. So something like this rig that we see in the upper right. Okay, so very, very different from this idea of keyframing, really letting an actor drive the animation. And finally, we have procedural animation. So something where the animation or the motion doesn't come from a human making adjustments, and it doesn't come from motion going on in the real world, but it comes from something purely algorithmic. Right? So a really good example would be physically based simulation. I write down Newton's laws of motion into the computer, and I tell the computer to solve this system of equations, and out pops this very interesting and beautiful motion. This is a way to get a lot of complexity in animation without a lot of work. And we'll talk about that in our subsequent lectures. Okay, so how do we translate keyframing into the digital setting? Well, it's, again, very much the same as with hand-drawn animation. The basic idea is we specify just the important events. The computer goes in and fills the rest via interpolation or approximation. Importantly, the events, so here I'm showing a bouncing ball. Okay, if I want to animate a bouncing ball, I start out at some location. I have a second keyframe where I bring it down toward the ground, make contact with the ground. I have a third keyframe where I move it up, another one down, another one up. And then I ask the computer, okay, please interpolate these locations. Give me some points in between my keyframes. In general, the events don't just have to be positions. I can actually interpolate any attribute I like. I could interpolate colors or light intensities or camera locations, camera zooms, various geometric transformations, and so forth. And once you start thinking this way, once you realize, the computer can fill in keyframes for all these tons of different attributes, you can again build up really rich and interesting animation very quickly. Okay, so the key question then is, how do we interpolate data? How do we do interpolation between keyframes? For this, we can go back to a very old idea of spline interpolation. So a very long time ago, if you wanted to draw a nice curve, let's say you were trying to do architecture, design a ship or something like this, and you wanted to draw a nice smooth curve, you would use a physical object called a spline, which is maybe a thin strip of wood or thin strip of metal that resists bending. Right? So what happens to this thing if you just kind of let it go is it just goes completely straight like a ruler. And if you manipulate its endpoints or you put little points in the middle like you see in this picture, then it's going to bend this spline into some new shape, but it's going to try to be as flat as possible. It's going to try to be nice and smooth. Okay? And so you can think of this spline as really interpolating the positions of these little objects that are hanging off of it. More abstractly, interpolation, as we've talked about before in this class, is the basic idea of sort of connecting the dots. I have some data points, and I want to come up with some continuous function that passes through these data points. One of the simplest strategies is to use piecewise linear interpolation. So just connect the data points by straight line segments. This is really simple, right? Easy to write down, but not always the best thing to do for animation because it's going to have really rough motion. If we ask, how quickly is this curve accelerating over time, right, what does that look like? Well, the velocity is the derivative of the curve. The acceleration is the second derivative of the curve. So at these sharp points, we're getting kind of infinite acceleration. And this looks really unnatural. So what we can do instead is, there's no reason we have to use piecewise linear functions to interpolate our data points. We could say take polynomials, right? So rather than connecting by little linear pieces, maybe we connect by quadratic pieces or cubic pieces that try to interpolate or maybe just approximate a few data points. Okay? With the basic idea that we want to get better continuity than piecewise linear interpolation. In general, a spline, when somebody uses the word spline in mathematics or computer graphics, they mean any piecewise polynomial function. Okay? So in one dimension, spline interpolates data over the real line. So we might have function values fi that occur at times ti. These times are also sometimes called knots. So we have knots in the spline, and just to keep things kind of orderly, we put ti as a value less than ti plus 1, right? So these are ordered times or ordered knots. Fi are the values. And interpolates just means that the function exactly passes through those values at the given times. Okay? So if the function f is interpolating the data f sub I, it means that f of ti is equal to fi for all I. The only other condition is that the function is a polynomial when we restrict it to an interval between two knots. Okay, so for any t between ti and ti plus 1, the function f can be expressed as the sum of some constant coefficients ci times the time t to the j, okay, where d is the degree of the polynomial, c are the coefficients. Quite often in computer graphics and numerics, people use cubic splines a lot. You'll hear a lot of people talking about cubic splines. Why? It seems at first a little arbitrary. Why am I talking about cubic splines rather than quadratic or quartic? And one reason is that piecewise cubic splines give exact solutions to the elastic spline problem under the assumption of small displacements. So if we think back to this idea of a physical spline, one that's made out of a strip of wood or a strip of metal, right? We could ask, can I predict exactly how this thing is going to look? Well, if I bend it just a little bit, if I pull the knots just a little bit away from the straight configuration, then the curve that I get can be almost exactly described by a piecewise cubic spline where the polynomial on each interval has degree 3. Okay? More precisely, what do I mean by it gives this exact solution? More precisely, among all curves that interpolate the given set of data points, it's going to minimize the norm of the second derivative of that interpolating function. Okay? This is not quite the same as saying that it minimizes the curvature of that curve. The curvature is not quite the same as the second derivative, but for small displacements, these are very close. Okay, so that's very interesting, but in some sense, who cares? Like, why is it so important that I match the behavior of a physical spline? Right? We're on a computer, and not only that, we're interpolating motion in time, not in space. So why is it important that my digital spline behaves like my physical spline? I don't know. For one thing, it's that, well, those splines look pretty nice. Maybe another motivation is just pragmatic. Cubic splines have really nice, simple closed forms, decent continuity. They have a small number of degrees of freedom, kind of easy to manipulate and kind of predict what will happen. There are plenty of good reasons to choose other kinds of splines. For instance, there's something called a NURBS curve, a non-uniform rational B-spline, which is useful if you want to represent exact shapes like circles and ovals. There are other curves like clothoid curves, which are often used in very special applications like design of highways because they have special properties about their acceleration. They give you the least jerky motion. If you're driving around in a car, you want to drive along a curve, your criteria for what makes a good curve is different from I'm looking at it in an illustration program or I'm using it for computer animation. Also, another important reason why we have a fairly low degree spline, fairly low degree polynomials, is something called the Runge phenomenon. Okay? So it's really tempting if I have a lot of data points to say, wait a minute, I have a lot of data points that I want to match. Why don't I use a really high degree polynomial that just goes right through them? Or why don't I use a higher degree polynomial because I get higher degree continuity? Right? My first derivatives, second derivatives, third derivatives, fourth derivatives will all look nice. Well, something that's not obvious when you start doing this is that if you use really high degree polynomials to interpolate data, actually you can get really, really bad behavior. You can get these wiggles or oscillations. Or similarly, if I'm trying to approximate some smooth function by a polynomial, as I just naively increase the degree of my polynomial approximation, my Taylor series approximation, okay, at first it looks okay. So I started out with, kind of low degree. I'm going to increase the degree of the polynomial. This is going to get closer and closer to the target function. But as I go up, I notice that near the endpoints, I get these oscillations, and they kind of get, wilder and weirder as they go on, even though overall my function is doing a better job at 0 of approximating the target function. Okay, so generally, high degree polynomials are something that you want to avoid when you're approximating data or when you're approximating functions, because even though they behave nicely kind of in some local neighborhood, they start to have these wild oscillations as you get out further from that center point. Okay, so if we stick with these, reasonably nicely behaved cubic polynomials, how can we fit a cubic polynomial? So let's consider a single cubic polynomial, p of t equals at cubed plus bt squared plus ct plus d. And let's say that we want it to interpolate some data. In particular, we want it to match some given endpoints. Okay? So I have these 2 points on the left and the right, and I want to find a cubic polynomial that matches those 2 points. one thing that's important to realize, that maybe the first thing we should realize is, well, actually, there's not a unique solution here. There are lots of different possible coefficients, a, b, c, d, that will give me a polynomial p of t that hits these two endpoints. And I've drawn a few of them here. Okay, so in general, when we talk about interpolation and we talk about splines, it's important to think about degrees of freedom versus constraints. How many parameters do we have in the function that we're using to interpolate versus how many conditions or constraints do we have? How many things does that curve need to satisfy? And if we have more degrees of freedom than constraints, as we do here, right? We have 4 parameters, a, b, c, d. We have 2 constraints, 2 endpoint constraints. Then the solution won't be unique. We won't have actually said what the interpolation looks like. If we have more constraints than degrees of freedom, then in general there won't be a solution. We can't actually find a curve that does what we want, that maybe interpolates our data. Okay? So let's think about this for our cubic curve. All right, why are there so many different solutions? Well, again, cubic polynomial has these 4 degrees of freedom, a, b, c, d. We only need 2 degrees of freedom to specify the endpoints. Right? So again, if we have this polynomial p of t, then at time 0, we want it to be equal to the first point, p naught. At time 1, we want it to be equal to the second value, p1. Okay? If we plug 0 into our expression at the top, we get a times 0 plus b times 0 plus c times 0 plus d equals p naught. And so we can conclude that the coefficient d must be equal to p naught. If we plug t equals 1 into our polynomial, then we get a plus b plus c plus d equals p1. Okay? So what we've done essentially is turn this into 2 linear equations in 4 unknowns. Right? And so that's not enough to uniquely determine the curve. By the way, this is generally going to be the flavor of what happens when we're fitting polynomial curves to data. It seems a little strange we ended up with a linear system because we had a cubic polynomial, right? But the point is, the degrees of freedom, the constant coefficients in our polynomial, well, they're constants in the polynomial. So if we plug in any particular value of t, we get an expression that's linear in, well, in this case, a, b, c, d. It's in generally linear in the coefficients. And so this question of whether we can fit a given polynomial curve to a given set of data ends up being a linear algebra problem. Can we satisfy this set of linear equations? Okay? So given that this is unconstrained, what else might we ask about for this curve? What other constraints might we add? So what we can do is we could also try to fit the curve, the cubic curve, not only to the endpoints, but also to a set of derivatives at the endpoints. So a picture like this. Right? I want a curve where the value at time 0 is p naught, the value at time 1 is p1, and the first derivative at time 0 is u naught, and the first derivative at time 1 is u1. Here's an example of a curve, a cubic curve that satisfies those conditions. Is it unique? Well, once again, we have these same conditions that p of naught equal p0 implies that d is equal to p0. P of 1 equals p1 implies that a plus b plus c plus d is equal to p1. And also, if we take the derivative of p of t with respect to t, we get what? We get 3at squared plus 2bt plus c. Okay? If we now plug t equals 0 into that equation, we get p prime of 0 is equal to u naught. That's the constraint we want. We want the derivative at time 0 to be equal to u naught. And we want the derivative at time 1 to be equal to u1. Okay? Well, the only thing that remains if we set t to 0 is c, and so that's the same as saying c equals u naught. The only thing that remains if we set t to 1 is 3a plus 2b plus c. We want that to be equal to u1. Okay, so now it looks like we're in better shape. We have 4 linear conditions on A, B, C, and D, and 4 unknowns, A, B, C, D. So we can solve this system to find a unique curve that satisfies these constraints. Does this system always have a solution? Right, that's the one thing we would still have to check. It's not true that n equations and n unknowns is always solvable, but in this case, you can check that it is. And importantly, it's not going to depend on the data. The solvability of this linear system doesn't depend on the values P0, P1, U0, and U1, right? Only on the structure of the linear equations. So we can always interpolate endpoints and derivatives. Okay, so let's go ahead and do this. How do we view this as a linear system? So we have 4 equations and 4 unknowns. And if you flip back and forth between this slide and the last one, you can kind of see that this can be expressed as this matrix equation, right? If you multiply out this system, you'll get those same 4 equations we had before. And so we just want to solve this 4x4 system for A, B, C, D. So often, this is the game we will play. Each condition on a spline leads to a linear equality. Hence, if we have m degrees of freedom, we're going to need m linearly independent conditions to determine the shape of that spline. Okay, so now, rather than just considering a single cubic curve, let's consider a piecewise spline made of cubic polynomials p sub I. For each piece of this spline, for each interval between 2 knots, we want a polynomial piece pi to interpolate the data at both endpoints. Just as before, right? We want pi of ti to equal fi, and pi of ti plus 1 to equal fi plus 1 for all of our segments. We also want the tangents to agree at endpoints. Okay, so we said before we can kind of assign or prescribe the derivative of the polynomial in an interval. And what we're asking is that the final derivative of one interval equals the beginning derivative of the next interval. P prime of ti plus 1 is equal to P prime I plus 1 of ti plus 1. Okay? And let's go for gold here. Like we already are saying that the derivatives and the positions agree at the endpoints. Why don't we also ask that the second derivatives agree at the endpoints? Why not? Make it even kind of a smoother curve. So we can say that P double prime of ti plus 1 is equal to P double prime at I plus 1 of ti plus 1. Okay? Can we do this? Can we get a curve that is C2 continuous, that interpolates a given set of data points, that has first derivatives that are the same at each knot, and has second derivatives that are also the same at each knot? If they have the same first and second derivatives at each knot, then they actually have a second derivative that's well-defined everywhere on the curve, because each little piece is cubic, and each little piece is a polynomial. Okay? Well, let's see. We should really be thinking about this in terms of linear algebra. So how many equations do we have at this point? Well, let's see. We have 2n plus n minus 1 plus n minus 1 equals 4n minus 2 equations. How did we get that count? So let's see. Our first set of conditions says that for each piece, for each segment, I have 2 constraints. The left endpoint is equal to some value, and the right endpoint is equal to some value. So that's 2n. For the first derivative condition, I want the right end of one interval to match the left end of the next interval in derivative. Okay. So how many interior points do I have? I don't have that condition at the very first point and the very last point. Right? So I really only have n minus 1 conditions. Okay? And similarly for the second derivative, I have another n minus 1 derivative. So I have 4n minus 2 conditions, And how many degrees of freedom do I have? How many degrees of freedom do I have? So for each cubic polynomial, I have 4 degrees of freedom, A, B, C, and D. Right? And so it sounds like I have 4n degrees of freedom. So I'm not quite constrained enough. I have to somehow decide what to do with the rest of these degrees of freedom. One thing I could do is just pin down the remaining degrees of freedom by setting the curvature to 0 at the endpoints. Just saying when I enter the curve or I exit the curve, I'm just going straight. Curvature, I really mean the second derivative here. Okay, and that's for whatever reason why we call this a natural spline. Okay, so that's interesting. So now I have a big system of linear equations, 4n linear equations in 4n unknowns. I probably don't want to have to solve that by hand, but I could ask my computer to solve that for me and get this nice, beautiful curve. So that's one way we could do it. What is kind of the right way to do this? What's the right way to interpolate data? What could we want, right? What are properties of a good spline? Well, we've talked about one key property already is interpolation. We might want the spline to exactly pass through a given set of data points. We've kind of talked about continuity also to get this curve to look nice and smooth to avoid having jerky motion in our animation. We might like it to be fairly differentiable, especially if we're thinking about accelerations. That's something that we can kind of see in animation, or we can feel if we're driving in a vehicle, we can really feel the acceleration. So to get a nice curve, we'd really like that acceleration to be pretty smooth. So we could say we'd like a curve that's at least twice differentiable everywhere. Another property that turns out to be pretty important and useful in practice is locality. So if you imagine you're trying to edit this curve, you're trying to move it around or change the animation, it would be nice if moving just one data point, one control point, doesn't shift and move around the shape of the whole curve. Think about this in the context of animation. I have an hour-long animation, and I want to tweak slightly something that's going on in the first minute. Well, that really shouldn't affect something that happens an hour later, right? Okay, so those seem like pretty natural properties. How does our natural spline do on each of these properties? Let's see, does it interpolate the data? Well, yeah, by construction, that was one of our basic constraints, that the value of the curve at the knots is equal to the given data points. Does it have good continuity? Is it at least twice differentiable everywhere? Well, yeah, again, by construction. We said that the right endpoint of an interval has the same second derivative as the left endpoint of the next interval, and each piece is a polynomial, so inside each segment we have, infinitely many derivatives. What about locality? If I think about the way we set up that natural spline, if I move one of the data points, does it have a local effect on the shape of the spline, of the definition of the spline? So the answer is maybe not completely obvious, but the thing to think about here is that we have this big collection of 4n linear equations, and all these equations are coupled, meaning I kind of have to solve them all at once. I couldn't just go in and solve one of those equations by itself or 4 of those equations by itself. They're all interacting in some way. Okay? And that kind of tells you that this natural spline is really not going to be local. All these degrees of freedom are kind of glued together because we have these relationships between adjacent segments. Okay? So what we see is we got 2 out of the 3 properties that we wanted. So let's see if we can do better. Let's go through. There's lots of other types of splines we could consider. And to kind of spoil the punchline here, what we're going to discover is there's really no free lunch with cubic splines. We can't simultaneously get all three properties: interpolation, continuity, and locality. You have to pick two. Pick the two that you like the most or need the most in a given application scenario. Okay? So let's look at Bezier splines. We actually talked a little bit about Bezier splines already in our introduction to geometry. Right? We said Bezier splines are linear combinations of what are called the Bernstein polynomials. So another way of thinking about this more geometrically is to say each cubic piece of our spline is specified by endpoints and tangents. Okay? So we have endpoints F, and we have these blue lines, these tangents. And when we talked about Bezier curves, we kind of said, if you're drawing, let's say you're drawing a Bezier curve in some kind of illustration program, then generally you'd click on a black point, you'd drag the cursor to a white point, and then you'd click on the next black point and drag the cursor to maybe not to the white point, but the point on the opposite end of that second blue segment, okay? And so what you're basically doing is you're tracing out a little control polygon for that Bezier curve. The Bezier curve is going to be a nice smooth curve that sits inside the convex hull of the first two black points and the first two white points. Another equivalent way to look at that is you're giving the endpoints and the tangents. And that's called the Hermite form of the curve. So Hermite and Bezier are giving you essentially the exact same kind of curve with more or less the same data, but in the Bezier case, you think of it as 4 control points, really locations in space, and with Hermite, you think about it as points and tangents. And it's really easy to convert between this data. You basically just take the difference of the control points to get the tangents. If you really sit down and write it out, there might be a factor of 2 in there or something like that, but that's the basic idea. Okay, so these curves, Bezier curves, are commonly used, very commonly used for 2D vector art. Any kind of illustration program you use is going to be using Bezier curves. All the kind of standard file formats, SVG, PDF, font formats, are using Bezier curves of various degrees, usually quadratic or cubic Bezier curves. For cubic Bezier curves, the thing we want to know is, can we get tangent continuity? Is it possible to draw a Bezier curve where the derivatives agree from one segment to the next? Well, yeah, sure. I mean, especially if we think about this in Hermite form, no problem. We just set the tangents to the same value on both sides of the knot, just like we did for our natural spline. So for instance, in the picture above, at the point F1, we have tangent continuity. At the point F2, we did not have tangent continuity. Right? So we don't have to have tangent continuity with a Bezier spline, but we can easily get it. Okay? So more precisely, when we have a Bezier curve, we want the endpoints to interpolate the data. We want, at each knot, we want to pass through a particular value f. And we also want tangents to interpolate some given data. Right? So for each little segment, let's say we look at the ith segment, then the derivative at the left endpoint, p prime sub I at ti, is equal to some given value u sub I, and at the right endpoint, pi prime of ti plus 1 is equal to some other value ui plus 1. Okay? So how is this different from our definition of a natural spline? Right, there we also had some kind of condition on the values of the derivatives at the ends of the intervals. Okay? Well, there, the tangents didn't have to match a prescribed value. They just had to agree. We didn't care what the derivative was at the endpoints as long as the derivative at the right side of one interval matched the derivative at the left side of the next interval. Here we're doing something different. We have some fixed data that the derivatives have to match. Okay? So different kind of spline. how many conditions do we have overall? That's it. That's all the conditions we have on this Bezier spline. How many conditions do we have overall? Well, this time it's really easy to account. We have, for every interval, we are fixing its 2 endpoints and its 2 derivatives at those endpoints. So we have 2n plus 2n is 4n conditions. And we still have 4n degrees of freedom. Okay, so this completely determines our Bezier spline. What properties does this curve have? Let's see. Does it have interpolation? Well, yeah, by definition, by the first condition. It will, by construction, pass through the values we want it to pass through. Does it have locality? Well, sure, and this is the really interesting one, in contrast to our natural spline. In this case, all I did really was I took each segment kind of by itself and I said what its 2 endpoints should be and what its 2 derivatives should be. As we saw when we first started talking about a cubic polynomial, a cubic Bezier, that's enough to determine the shape of that little segment. I don't need to know at all what my neighbor is doing. Okay? So with the natural spline, we had this system of equations that all interacted with each other. With the Bezier spline, each little piece I could solve for on its own. And so what that means is if I start moving around some of these data points, I move around fi or I move around ui, then I don't have to solve a big system. I don't have a global change to the function. All I have to do to make sure that I continue to have continuity is to make sure that the data that I give to adjacent segments agrees. Both of them are matching the same value fi and the same derivative ui. Okay? So it has interpolation, it has locality. What about C2 continuity? Does this curve have nice acceleration? Well, no, we didn't say anything about the second derivative. Right? The second derivative could be totally awful. We might not want to really travel along this curve. So again, what we see is we have 2 out of the 3 basic properties that we might like to have. All right, so let's take a look at a third kind of spline, a Catmull-Rom spline. So sometimes it makes sense when you're working with a spline, when you're maybe drawing something, illustrating something, sometimes you might want to specify the tangent, right? You want to get this kind of precise control over just how the curve bends. But for a lot of tasks, this is annoying. What you really just want to do is give some values, give some points, and say, please give me a nice curve that passes through these points. That's maybe the more basic task of interpolation. Please give me a nice interpolating curve. And that's the idea behind a Catmull-Rom spline. So Catmull-Rom spline is a kind of specialization, if you like, of a Hermite or Bezier spline that can be determined purely from the values. Okay? And the basic idea is illustrated by this picture on the bottom right, which is to say I only know the data points. Nobody's provided me with any tangents. So I'm just going to use the difference between the positions of neighbors to decide what my tangent should look like. So if I just hand you a bunch of data points, fi, f1 through fn, or fn plus 1, then I'm going to say the derivative at node I is fi plus 1 minus fi minus 1 over ti plus 1 minus ti minus 1. How much did the value change over the time, over those 2 intervals? Okay? And from there, I just do the same thing that I do for my Bezier spline. I just say that the endpoints of each segment interpolate the f values. The tangents of the 2 endpoints are given by the data that I just computed. Okay? So this has all the same properties as any other Hermite or Bezier spline, right? Locality, and so forth. This is something that's really commonly used to interpolate motion in computer animation because, again, especially when you're talking about motion, it may not be clear what velocity you want, right? You just want to set the camera down at different locations in space and get a nice interpolation. So there's lots of different variations of this kind of spline that give even smoother, nicer motion, but Catmull-ROM is usually a pretty good starting point to get some basic animation. Okay, so let's take a kind of systematic look at what kind of splines we have so far, and do they kind of have the properties that we want. We said there are three things that we care about: the interpolation property, we want C2 continuity, and we might want locality. The natural spline satisfied two of these, interpolation and continuity, but it wasn't local because we had to solve this big linear system. The Hermite spline was interpolatory and local, but it didn't have C2 continuity. We didn't say anything about the second derivative. And so just looking at this table, this naturally suggests, well, it feels like there should be a third option. There should be a kind of spline that has C2 continuity, has local control, but doesn't interpolate. What does that mean? So that's the idea of a B-spline. So the idea with a B-spline is that sometimes we can get better continuity and local control by sacrificing interpolation. We actually saw that a little bit with subdivision surfaces when we talked about geometry. So, for instance, Catmull-Clark and loop subdivision surfaces have local control. If I move one of the vertices around, it really only deforms a local region of the surface. It aims to have C2 continuity. At most points, the limit surface will be twice differentiable. But it's not interpolatory. So if you look at any of our pictures of subdivision surfaces, the limit surface doesn't pass through the control vertices. So that maybe makes it a little counterintuitive for modeling. Well, a B-spline is a same idea, but actually lower in dimension, easier to think about, right? So B-splines can be manipulated locally. I move one vertex and it just changes a little piece of the curve. They have good continuity. They're twice differentiable. But as you can see in this picture, they don't pass through the data points. They're not interpolatory. They just approximately follow the data points. Okay. How do we define a B-spline curve? Well, we can define the B-spline basis recursively. So the way we're going to do this is much like we originally, in our lectures of geometry, talked about Bezier curves as linear combinations of Bernstein polynomials. B-splines are going to be linear combinations of B-spline bases. The first basis, B sub I1 of t, is very, very simple. It's just 1 if we're inside the current interval and 0 if we're outside the ith interval. So it looks like this. So if we have a long curve with lots of knots, bi is going to be non-zero only on that interval. Okay? And so from then on, to get higher order B-spline bases, we just combine lower order bases. So we already have bi1. To get bi2, we take a linear combination of some bi1s. In general, bik of t is equal to t minus ti over ti plus k minus 1 minus ti times bi k minus 1 of t plus ti plus k minus t over ti plus k minus ti plus 1 bi plus 1 k minus 1 of t. Okay, what are we doing here? We're just doing linear interpolation. We're just linearly interpolating between two of the lower order B-spline bases. Okay? And then the B-spline itself is a linear combination of these bases, where d is the degree of the basis. Right, so bi1 are these piecewise constants, bi2 are going to be piecewise linears, and so forth. Okay, so if we go back to this table, what we'll find is that for cubic B-spline curves, these are going to be C2 continuous by construction. They're going to be local by construction because we're just adjusting coefficients in some basis. but they're not going to have the interpolation property. There's nothing in this construction that guaranteed they would exactly pass through the given values. Okay, and so the point of this table is to say, when it comes to splines, there's no free lunch. There's always some property that you have to give up on, and you have to think, for a given task, which properties matter the most. Am I doing illustration? Okay, then maybe local control is really important, and interpolation is really important, but I'm willing to sacrifice a little bit on continuity. If I'm doing animation, maybe I want really good locality and continuity, and I don't care maybe so much about perfect interpolation, right? And generally, this is a situation that you will face in numerical methods and in discretization, that there's no best method. There's always some kind of trade-off. And rather than clinging to what you consider to be the best, it's good to understand these trade-offs so you can pick the best method for the task at hand. Okay? All right, so hopefully we get at this point. Splines are really great. There's lots of different ways of doing it. But what exactly are we interpolating? What is this data? What are these values f that we interpolate in order to get animation? And as I hinted at before, that data could be anything. It doesn't have to just be positions, but it could be, for instance, in the case of a camera, I might have positions. I do want to interpolate the position of the camera over time. That's how I fly around this city. But also to generate an animation like this, I can't just be talking about how the position changes over time. I also need to be talking about how the orientation of the camera changes over time. So maybe I could animate the frame of the camera, the direction that I consider to be right, forward, and up, right? For the position, if we just think about where the camera is in space, what I'm really doing is I have 3 different values I'm interpolating: the x-coordinate at each moment in time, at each keyframe, the y location, the y-coordinate at each keyframe, and the z-coordinate at each keyframe. I interpolate all 3 of those to get the location of the camera. Okay? Really easy way to make a nice animation, even if I just have a static piece of geometry. In a character animation, if I have a rig or a kinematic chain that describes the configuration of a character as a tree of transformations, right? Much like in your fractal trees, and then I could be animating the degrees of freedom in those transformations. If that tree has rotations in it or translations in it, I can now have, rather than just constant values, constant angles, or constant offsets, I have a spline that I interpolate over time to get motion. And in this rig, you can see we have a really complicated tree of transformations, lots of different degrees of freedom, and by interpolating those degrees of freedom, we get all sorts of interesting animation. Okay. And so what you see is the computer is now doing all the work of doing the in-betweening, right? The animator just has to set the keyframes, but actually now, because there's so many degrees of freedom, there's so many complicated transformations in this rig, even setting those keyframes is a lot of work. And so for this reason, people come up with different techniques for specifying even those keyframes. One of those techniques, really important one, is inverse kinematics. So in both animation and robotics, this is a technique that you want to use if you say, okay, my character has a goal, or my robot has a goal. It wants to go and pick up an object that's on the desk. Well, I'd really rather not have to figure out what is every single angle in the arm at every moment in time, or every keyframe in time, in order to make that motion happen. Instead, what I'd like to say is, please put the hand here at time 1 and somewhere else at time 2, and then go ahead and figure out automatically how I should set all those other joint angles, all those other degrees of freedom. How do I get the computer to do that? How do I get the computer to figure out all those other variables? Well, the basic idea is to use some kind of numerical optimization or descent. And we will talk about that in a subsequent lecture. We'll talk about optimization and how we can apply that to things like inverse kinematics. Another technique that's quite popular in computer animation is something called skeletal animation. So some of the characters we looked at before looked a lot different from Cube Man. If we think back to this really kind of simple character we made out of cubes, it had these disjoint pieces that rotated and translated around independent of each other. They didn't deform in any way, whereas real characters, human beings, animals, and so forth, they had this much more nice organic deformation. How do you get that to happen? Well, the secret is that under the skin, you still have kind of a rigid skeleton. You have a collection of rigid pieces, these bones, that you can see in the image on the left. And those get transformed in the usual way. You apply some kind of rotation around some joint, right, to get a new configuration of the skeleton. That skeleton then drives the configuration of the character. How does it do that? Well, each bone has a weight function associated with it. So for each bone, I can assign to every, let's say, vertex of a mesh, how much influence that bone has on that vertex. To then transform the vertices of the mesh, I might take, let's say, a linear combination of all those transformations. So for each bone that affects that vertex of the mesh, I apply the bone's transformation to that vertex. I get a bunch of different vertex positions, and I add them all up and average them to get this deformed location. So I get this smooth blend between the motions of different bones. That's the most basic idea. That's called linear blend skinning. But there's lots of more sophisticated techniques that people are still thinking about. Places like Pixar are thinking about how to do that kind of deformation while making things look physical. So something that for instance, with tissue, with muscle, is that it tends to preserve volume. It doesn't compress very much. So how do you get that to happen as you're deforming the shape? Another nice technique is what are called blend shapes. So somebody who's doing 3D modeling can go in and model some basic poses, let's say of the face, happy, sad, sleepy, awake, and again take linear combinations of the vertex positions in those meshes to get an animation. Where do the splines come in? Well, the splines are interpolating the coefficients in this linear combination. So I have a function that represents how happy am I over time. I have a function that represents how sad I am over time. Each of those is represented by a spline, and I add up those coefficients times the blend shapes. Okay. All right. So that's it for spline animation. You can see that's already giving us some pretty nice, beautiful animation, but taking a fair amount of work because we have to set all these keyframes still. We have to manipulate this complicated rig. So what we're going to see in our next few lectures is how other modes of animation can really help to reduce the amount of effort. We're going to look at how we can use data, acquire things from, let's say, motion capture, and also how we can use physical simulation. How can we just set an equation in motion to get really rich and complicated animation? All right. Talk to you next time.